Now, is this usable or useful to attacker? And is this some way to do fragmentation or source routing over IPv4? Well, maybe. We didn't actually test it, but it points to something that's possibly interesting. And certainly inferring meaning from the lack of a protocol unreachable is not reliable. The lack of a negative doesn't establish a positive. Although like in certain beta 2 builds, an IPv4 packet with protocol 43 would cause a blue screen of death. And IPv4 packet with protocol 44 would cause some other different problems on the network. Now, there were some other protocols that showed up as available. These were associated with tunneling. And based on the IP scans, it looked like IPv4 over IPv4 and IPv6 were available. IPv6 over IPv4 and IPv6, and GRE over IPv4. But we didn't actually investigate the availability of most of these. But this is what appeared to be available. And there's a couple other tunneling mechanisms that we know of in Vista, Torito and the IP6 tunnel mode. And this means that there's more tunneling available in Vista and then XP. And this is an area of concern due to the possibility that security controls be bypassed by this tunneling. The security controls, security devices don't know to look inside for the real content. And we do know that on Vista, the Torito component will refuse to start up unless there's an IPv6 firewall in place. So that's a sensible security precaution. Make sure there's a firewall there. And there may be the same safety check for IPv4 over IPv6. And that's because of this right here, is that IPv4 over IPv6 only showed up when the firewall was on. It didn't show up when the firewall was off, which is kind of the opposite of what you normally expect because the firewalls do filtering. So that's one possible explanation as to why we get that result. Okay. Already did that one. Okay. We did a TCP port scan as well, and when you do the port scan, you might get different results depending on where the scan is coming from and what the network profile is. Coming from the same subnet with the private profile, we found that almost all ports were filtered. We didn't get any synax, we didn't get any resets. Although one port, 5357, corresponds to web services for devices, was available over IPv4 and IPv6. We were able to connect in. Web services for devices is a way for devices on the network to find Vista and to communicate. Incidentally, we did get the same result from the Torito interface scanning from the internet. That's prior to the fix that Microsoft did. We also did a UDP scan, and we found that for all ports, we didn't get any response, which means it's either filtered or open. There isn't any protocol-independent way to tell the difference between open and filtered under UDP. But based on just this firewall rule state and NetStat, the protocols I list there may be available. Okay, one of the things we ran into is that Vista rate limits ICMP v4 and ICMP v6 error messages, something like no more than 1 second, which means we had to slow down our IP protocol and UDP port scanning. And that's because those depend on seeing each and every ICMP error message that's produced. If you can't do 2 probes because you'd at most get 1 unreachable message back. And this meant it took us 18 hours to do a simple port scan over all ports. So this will slow down legitimate and malicious scanners unless there's some way to work around it. such as using multiple sources, say. Just a few miscellaneous observations from Vista. By default, does not respond to pings, unlike XP. Although if you turn on file sharing, it will. The IPv4 ID range, Vista only uses half of it for some reason or other. It only uses 0 to 7 FFF. I think I did one too many Fs there. And it does use the range sequentially, so it still should be possible to do host counting behind an AT. And the framework port range has changed. The default is 49152 to 65535, which is different than XP. You can change that manually in NetShell. Okay, and now we'll go into some of the what we found from IP and TCP segment reassembly. Just as background for those that aren't familiar, it's possible, though not legitimate, to send an ambiguous sequence of IP fragments or TCP segments. For example, you send this different data for the same part of the same packet. Send it in different fragments, and the different TCP IP stacks will interpret these in different ways. That's because the TCP IPv4 or IPv6 specifications say how to treat these. But I remember being specifically disappointed that the IPv6 specification, when I read it for the first time a few years ago, didn't say what to do with these kind of packets. It left the ambiguity in there. And this creates a challenge for IDS and IPS that are network located, since those need to predict and match the behavior of the recipient system. Otherwise, it could be analyzing something entirely different than the recipient scene. So it needs to look at it to avoid evasion. And for more information on this type of attack, you can read the classic paper by Thomas Petasic and Tim Newsham. Just as an example of this ambiguity, here's there's 4 overlapping TCP segments, and they're the data doesn't always, the content doesn't always match up. And for Vista, we'll say think this says this is bad. XP would say that is bad, and Linux will say that is mad. So there's an example of three different ways to interpret the same sequence of fragments. For Vista, we did an empirical analysis or empirical study of how this reassembly worked, and we found it is different than XP and other stacks. Old data is strongly preferred over newer data. This means that IDSs will have to adapt to prevent evasion. We also did this. We also did an empirical analysis for Vista and IP fragment reassembly. And again, we found that the behavior is different than XP or any other stack. And I guess this just goes to show that the stack is new. Although IPv4 and IPv6 will behave the same for Vista. Again, IDSs will have to adapt. Here's one example. You got 2 fully overlapping fragments, A then B. And in this case, XP and Vista will both prefer the old data, whereas Linux will prefer the new data. However, in a more general case, when there's partial overlap, the fragments don't line up neatly. In this case, XP will favor old, but Vista won't reassemble the packet at all. It appears that the state gets discarded. Although it is possible, though, for partial overlap to succeed, but the overlap must occur within the part of the packet that could already be reassembled, starting from offset 0. For example, here, when A comes along, B comes along, and those define the first 32 bytes of the packet, and then C comes along, which fits entirely within that. In this case, C just gets ignored. So this is kind of weird shape of reassembly. It's not like a simple rule. And this, and I do go into more details on this in the paper. I present like 64 test cases that we did. And so it looks like this behavior isn't based on an intentional policy decision. It doesn't seem like that to me. It looks like it's just whatever the code happened to do for this case, and it means a couple things. One is that this behavior is more likely to change just with any update to the code, and also it means that Microsoft doesn't appear to have been aware of the issue for NIDS, or maybe they don't care. I think it's the previous one. They just weren't aware. Talking to a named architect from that team, that is what the impression I got. It was just a casual conversation. Okay, and right slide here. Okay. Now I'll go into how we did our observations for the IP fragment reassembly for IPv4 and IPv6. IPv4 we took what's probably a classic approach, is in that the region that is fragmented ambiguously is the payload of a UDP packet. So then we ran a BlackHat as a listener on the recipient system. So when after the packet gets reassembled, if it will be reassembled, BlackHat will see the result. It'll show up there on the screen. And one of the things when you realize when you're coding the fragmenter is how do you set the UDP checksum, because you don't want to presume how the recipient is going to interpret the packet. And with IPv4, you can set checksum to 0, which means there's no checksum. That's your way around it. However, that doesn't work for IPv6, since with IPv6 the UDP checksum is now required. That means we had to develop a new approach. So for IPv6, we used the approach of sending a packet that, when reassembled, would generate an IPv6 error message. That is, we intentionally cause an error, but not until the reassembly completes. And that works because ICMP error messages will return the original packet. Well, in this case, the original packet is the packet as reassembled by the recipient system. And specifically, we use a destination option of type 9F. There is no such type defined, and that's exactly the point. And specifically, since it starts with binary 1-0, this the RFC for IPv6 requires that an error message be produced in that case. So that's how we ensured that we'd get the packet back, assuming that it gets reassembled at all. And this does take advantage of a new requirement in IPv6 that the full original packet must be returned, rather than just IPv4 is just only required that the first like 16 bytes of the included payload or something like that be included. Okay, now I'll go into Teredo. Just a background on how it works. Teredo was developed by Christian Huitma of Microsoft. It was commendably brought through IETF. It was published as RFC 4380, which was a standards track individual